looks like a completely random jumble of numbers and powers, just designed to be unsolvable. But what if it's not? So meet our monster. This is a 12th degree polynomial. That 12th degree just means its highest power is 12, and it has a whopping 13 terms in total, with some absolutely massive coefficients. And hidden somewhere inside all this chaos are 12 different solutions, or roots. Finding them? Yeah, it seems like a totally impossible task. All right, section 1, a monstrous polynomial. Our challenge is officially set. So how in the world do we even begin to tackle this beast? That brings us to section 2, the theorem. Because luckily, every great puzzle has a secret key. And for this one, it's a really powerful mathematical theorem. This is Murad Sultan Izawidi's theorem. Now look, we are not going to get bogged down in the formula itself. What's really important is what it does. Think of it like a special lens that helps us find a hidden set of numbers, we're going to call them S values, that basically reveal the polynomial's much simpler true identity. So here's our game plan, and it's pretty simple, kind of like good detective work. Step 1, we're going to apply the theorem 12 times, for every index from 0 all the way to 11. Step 2, this is going to give us our key S values. These are our clues. And step 3, we use those clues to rebuild the equation from the ground up, and finally crack the case. Section 3, searching for clues. Okay, the investigation officially begins. Let's start the hunt for those S values. We're going to start our search methodically, right at the beginning, with the first index, k equals 0. We take the numbers from our monster polynomial, we feed them into the theorem's formula, and what's the very first clue it gives us? 0. Our first clue is nothing. Huh. That's interesting. Definitely not what you might expect. But hey, it's just the first clue, so we keep going. And this is where it starts to get kind of strange. We run the theorem again for k equals 1, and the result is 0. We try it for k equals 2, still 0. Then for k equals 3 and k equals 4, you guessed it, the exact same thing. A very clear pattern is starting to emerge here. I mean, 5 times in a row, the theorem gives us a result of 0. Come on, that can't be a coincidence. This pattern of nothingness is actually telling us something incredibly important. A secret structure is starting to show itself. Okay, on to section 4, the pattern breaks. Because just when we think we know what's coming next, our investigation takes a huge dramatic turn. This is where we find our first real clue. So, this is the big moment. After a string of 5 straight zeros, what do you think is going to happen when we calculate our 6th value, S5? Is it going to be another 0? Not even close. The pattern absolutely shatters. The theorem spits out this colossal number, over 1.7 billion. This isn't just a number, my friends. It is a giant flashing neon sign telling us we found something vital. And then the mystery deepens. Just as suddenly as it appeared, the pattern of zeros immediately comes back. For k equals 6 all the way through k equals 10, the result is 0, 0, 0 again. It seems like our clues are pretty rare and incredibly valuable, but we've got one last calculation to make. At the very last step, for k equals 11, bam, we find our second and final non-zero clue. And it's another astronomical number. This time it's negative. And with that, our detective work is done. We have all the clues we need. Which brings us to section 5, the great simplification. Now, it's time to assemble our clues and finally crack this case wide open. This is where the magic really happens. So, what was the big deal with all those zeros? Well, this is the secret. Each one of those S's values corresponds to a term in the original polynomial, and an S value of 0 means that entire term gets eliminated. It just vanishes. We found 10 zeros, which means 10 of the 13 original terms are completely wiped out. And look at this. This shows the transformation perfectly. On the left, you have our original monster, and on the right, after we apply our clues, is what's left. The beast has been totally tamed. That sprawling, chaotic equation just collapses into this beautifully simple, elegant form. This chart really says it all, doesn't it? We started with a monster that had 13 separate terms, and by finding those hidden R's values, we slashed it all the way down to just 3. The true, simple form of the equation was hiding in plain sight the entire time. On to our final section, the final answer. The mystery is officially solved. With our simplified equation, we can now do what seemed impossible. And here it is, our final simplified equation with our two giant clues plugged right in. All that noise, all that complexity has just been stripped away, leaving behind only the essential core of the problem. And you know what? From here, the equation is surprisingly manageable. It's what mathematicians call a quadratic in disguise. Because if you squint, it just looks like a simple x squared equation, but with x to the sixth instead. And that means you can use pretty standard methods to find all 12 roots of the original puzzle. Case closed. You know, it really makes you wonder, doesn't it? This whole thing wasn't